No questions. No questions. Okay. All right. Okay. I'm an optimistic fool, so I'll take that as a good sign. On this handout I gave out last time, there's one problem from section 11.5, and part H talks about section 11.5. So I'm going to, actually I'll tell you what, let's do this. Before we get into section 11.5, let's do a quick review of cross product and talk about that very last problem, number 2 on that handout. Problem number 2. So who remembers what's the length of the cross product? It's actually a nice little formula analogous to the dot product.
UV sine theta.
Length. So the U, length of U, length of V, sine theta, just like dot product is U cosine theta. So that's just the length of the cross product. And I really hope you understand. I want 2 kind of definitions for multiplication of these vectors. One of them is scalar, and kind of corresponds to lengths of the vectors lying on each other. The other one's a vector outcome, which makes more sense. It's kind of a closed idea. If I do an operation on 2 vectors, I expect my answer to be a vector, possibly. At least one of my definitions of multiplication. So to do a cross product for real, if U was U1 I plus U2 J plus U3K, and V1, I mean V was similarly done, is that cool? V1, V2, V3. How would you set it up for this? Yeah. The matrix determinant, U1, U2, U3, V1, V2, V3. If you really hate determinants of matrices, you can try to memorize the formula in its full glory, right? The matrix definition is really just a way to remember the formula. That's it. It's not like, bless you, it's not like a matrix is somehow magically a part of this whole thing. It's just a way to remember the formula. It truly is. It does have some higher level stuff. If you're going to go to linear algebra, remind me, I think a couple of you guys had already had linear. Is that true? Has anybody had linear algebra? Yes, okay. So you guys might remember when you do a matrix and you get like a 0 row, you can interpret the answer geometrically. Is the answer a line? Is the answer a plane? Is the answer a point? That kind of thing. So this actually has some direct relationship to that. But we'll leave that alone. Let me ask you this one question. What would it mean if U cross, well, what's it mean if U dot V is 0? Yeah. Now, what do you think it would mean if U cross V was 0?
Parallel.
And why do you say that? Because remember, what's the answer? What's the definition of vector? What's that vector supposed to do? That's the answer. It's got to be perpendicular to both. So if they are parallel, in fact, if they lie along, let's say this is U and this big one is V, how many things are perpendicular to both? R2. How many vectors? R3. Good point. In R3. I like it. It's exactly what I want to see. This, right? This is perpendicular, but so is this, and so is this, and so is this, and so is this all the way around. Right? So there's an infinite number of vectors that are perpendicular. And that's why the answer actually comes out to be 0, because it can't resolve it. It says, well, shit, 0. I don't know. There's an infinite number of answers. Leave me alone. So we officially say there is no answer. How we do? The minute I give it a little bit of, there you go. Right, here's U, here's V. Now there's going to be a specific answer, right? It's got to be popping up out of this plane. Because of the fact, if U and V are at angles to each other, or at an angle, they're not lying on top of each other, don't they together define a plane? Does this define a plane? No, it could be this plane, that plane, this plane. That's what leads to the ambiguity of the answer. Okay, maybe. Yes?
Which answer is ambiguous? The cross?
Yeah, when it comes out to be 0, that means there's actually infinite solutions. There's too many possible things that are perpendicular to both.
So it's not parallel.
Yeah, they are parallel, right? And again, remember, I know these are lying on top of each other, but where is U? Where could U be? Anywhere, as long as it's actually pointing in that direction. Or could it be pointing back that way too, right?
Wait, so they don't cross each other?
How do you mean?
They're parallel they don't touch each other.
Because they point in the same direction or exactly the opposite direction of each other. Right? That's what parallel means.
Yeah.
Cool.
So, what are you talking about perpendicular?
Because what's a cross product answer got to be? The vector that is what to both? When I do a cross product, the answer is going to be a vector that is perpendicular to both. That's why I'm talking about it.
Oh, okay.
Yeah, cool.
Gotcha.
All right. What else is oh, so you guys could actually see it up here, of course. If it comes out to be 0, the angle between them must be 0 or 180 or pi. Yeah, I love it. Right? So you can kind of see it there also. Okay. So look at number 2. I like number 2. The funny thing is, I just talked about all these cross products. We're going to do number 2 two ways. We're going to do it the way I ask you. Find a vector orthogonal, and orthogonal is another name for perpendicular. Right? I don't know why. There's certain things in math that we want like 5 names for. And perpendicular is one of them. So find a vector perpendicular to u and v without using a cross product. And the reason I ask you to do this is because it's nifty to see the math directly working out. Because there's a whole other way to do it besides this matrix way. There's a whole other way to do it. And the answer to this, if I said find a vector that is perpendicular to both these, and this is always, it's rude when I ask this kind of question, but I say find a vector that's orthogonal to both, will that answer be the cross product?
Yes.
No. Sorry. Well, I appreciate you had the courage to say something. That's awesome. But why? The cross product has to be as long as what? This. If I find a vector that's orthogonal to both, it could be anything. At least as long as it's pointing in the right direction or directly opposite, right? You guys with me?
Mm-hmm.
The cross product is a vector. I think I define it this way in here. The cross product is, they have an angle of theta between them. There's a vector that is orthogonal to both u and v with magnitude this. So the answer I find to this one might not be the true cross product, right? Okay, maybe. Because the cross product is a specific vector that's orthogonal to both. The vector that points in the right direction and has length this.
But you're saying that that vector also orthogonal to both.
But so it's the cross product minus the length?
Well, if you do this, are you trying to think ahead about how to make this work to be the cross product? You can force it to have the right length, right? Well, first you can figure out the right direction. But let's try this problem out. How the hell do I do this then? I mean, can somebody tell me my answer is going to be maybe the w vector, right? And what are the components of the w vector?
W1.
I love it. W1, W2, W3.
So can we use dot product here?
Yeah, exactly. Why do I want to use dot product? Because dot product has a very specific outcome for orthogonal vectors, right? I want this vector to be orthogonal to both of these. So what does w dot u have to be? 0. And what does w dot v have to be? 0. If you start realizing what's going on, we have 3 unknowns, 2 equations. Can I solve that all the way?
No.
There will be a parameter, but that's just going to be the length. As I change my parameter, I can make it longer or shorter or point the other direction, right? So that's why so far this makes sense. I should get an infinite number of answers for orthogonal to these two, because it could be any length or pointing in either direction. One of those is the cross product, the one that's pointing the right way with the right length. How you guys doing? Yeah.
So basically, the cross product is just, if you take a plane, it's just whatever's perpendicular to that plane.
Yeah, and that plane is defined by those 2 vectors. But and again, just to make this point.
Yeah, so it's like you have 2 vectors like this, and then that makes this plane right here because these 2 vectors, and then it's just the cross product is just the vector that's.
It's the specific,
orthogonal,
and again, it's not a huge point, but it's a specific vector with a certain length and so forth, but it is going to be orthogonal to that plane.
Okay.
Exactly. 2 vectors define a plane, just like 2 points define a line. 2 vectors define a plane, as long as they're not lying on top of each other. then it wouldn't really be two separate pieces of information. It'd be one piece of information, right?
And it's like torque, where you take like you're trying to tighten a bolt. It's like you have the plane, which is, well, basically just like the cross. I remember in a problem that said the cross product was the torque of something. So if you wanted to apply the maximum force, you would use the orthogonal vector, the cross
And then
product.
your angle such that you get the maximum force out.
Yeah.
Okay. But you're right. It's sort of like the cross product is going to be normal to that plane. It's going to be orthogonal to that plane. Okay. So what does this look like? What does this dot product look like? What's the dot product of W and U? W, 1, sorry,
Negative
minus W2,
W. Negative 12 W3.
careful now, I'm doing it with W and U, right? So W1 times U1, W2 times U2, W3 times U3.
Oh,
So
yeah.
please, plus 3W3, right? So there's an infinite number of answers for that. Then I have one more piece of information.
What did you do?
So what is W dot U? What is this dotted with U?
Okay.
And of course it's just the components added together, right? That dot product definition just kicks so much ass. It's exactly what you'd hope with a multiplication rule would just multiply all the freaking components together. Right? You'd hope that a rule would have that, and it does. So WV would be what? W dot V?
5W1
Yeah, 5W1
plus W2
plus W2
minus 4W3.
minus 4W3. I like it. Now I don't know if you guys have ever had experience working out a problem like this where you only have two equations but three unknowns. Has anybody ever done that before? I mean, what has to happen here? I mean, you can solve this to a point. So what's like a good first step? So my two equations are W1 minus W2 plus 3W3 is 0, and 5W1 plus W2 minus 4W3 is 0. How do you go about solving that? You can set them equal to each other. Sometimes that won't really get you too far.
Like W1 is 0 and go there.
Well, we can.
Say again?
W1 is 0 and then try to solve it, but it's still.
Well, you don't know if W1 is 0, so you can't plug anything in for any of these because you don't know what they are.
Add them together.
Can we?
Yeah, one thing you could do, just because these want to go away, is add them together, right? There's a few different ways to approach this, but if we do add these together, what do I get?
6
Right, so isn't W3 equal to 6 times W1? Okay, cool. And then can't you plug that into either one of these and solve for W2? So the best you can do, since you don't have enough information, there's three things I don't know, I only have two pieces of information, is I can solve it to where I have one variable left, right? There you go. That makes sense. If I have two pieces of information, that should kill two of the unknowns, and I still have one unknown left. So it looks like I want to maybe put everything in terms of W1. I want W2 equals something to do with W1. Can you guys see that? So if I plug 6W1 in place of W3 into either one of these and solve for W2, I'll have W2 in terms of W1. Right, this is just solving systems of equations. This step here shouldn't be terribly evil. I want to kind of take us a certain way here, though. So here's one thing. W3 is 6W1. So if I plug it into this first equation, 6W1 in place of here, I get W1 minus W2 plus 18W1 equals 0. So I get W2 equals 19W1. Okay. And I wish I would have picked A, B, and C instead of W1, W2, W3, but oh well. I think I did it when I was doing it on paper last week. I forgot all about that. So let's kind of summarize what we got here. We actually have an answer. So remember, W is W1, W2, W3. All right, let's fill in what we know. What do we know?
W1.
W1 is what? It's W1. W2 is
19.
19W1, and W3 is 6W. If you say the word W enough, it gets really freaky. Now, How are we doing so far? So if I let W1 be 1, and I can make W1 whatever the hell I want to. And when I change W1, what am I really changing about my answer? Its length or its direction if I make it negative. Right? So if W1 equals 1, then one specific vector that's orthogonal to both of these would be 1, 19, 6. Now, as a review, I want you guys to actually go ahead and use cross product to find the cross product. And see if you can see the connection between what we found and what you found. So take these two and find what U cross V is. Let me know if you have some questions. So remember, if I want to do U cross V, I can do this if I want to. U1, V2, V3, V1, V2, V3. All right. And a little shortcut is you can put the I and the J and the U1, U2. I think it came out last time. We don't really use that last one, so no need to write it. Don't get confused. Or look up the equation in the book. Get that cross product. Remember the shortcut for this, doing the determinant? And if you think about it, it really all makes sense. I mean, if I do a determinant, it's going to be this minus this. So these are the positive directions, and when I go this way, it's the negative directions. The math is pretty, you can see how it's the same way either way. So what do I get here? I get
4,
yeah, I get 4i,
15J,
15j,
and 1K.
and 1k. And then if we go the other way, I'll get
minus 5.
minus 5k. Oh, I'm sorry, not minus. It's minus minus. So let's make it minus like that. Minus 5k, 3i, and
4J.
minus 4j. Yeah. And then we go ahead and change these signs. Add those together. I get I plus 19j plus 6k. That came out better than I thought. That's pretty easy to see the connection. Right?
Is it a coincidence?
Hmm?
Is it a good coincidence that we can...
Yeah, it won't necessarily come out to be exactly this. It came out to be the easy, let W1 be 1. Our cross product could have maybe needed this to be -2. Do you see what I'm saying? We just happened to get the easiest parameter value of 1 that matched up with it. It could have been -2i minus 38j minus 12k, and that would have been this with W1 equal -2. Right, it could be anything. Just happened to come out to the easiest one. Are you guys with me here? So this is an infinite number of solutions because it can be any length that will be perpendicular to both. Cross product is one specific one of those that has the correct length in the correct direction. Okay. Hopefully some of you guys see that that's kind of nifty. You use the definition directly. That's the definition directly. It's got to be orthogonal to both. Or you use the determinant kind of shortcut thing, and you get the same. You get a similar answer. A specific one of these answers.
So, since the cross product vector is so special, why would we need these vectors?
Because these represent anything orthogonal. So if I just need something orthogonal, and that's all I need, and I know a shortcut or I know something, then I can just get anything that's orthogonal. It doesn't matter. If I specifically need the cross product for some reason, then I need to get that. And of course, a cross product, if I'm doing physics or torque or whatever, it comes out with the correct magnitude. Like if I'm applying a force, I can't just pick anything orthogonal. I need the cross product because that got the correct magnitude. Right? If I'm just trying to create a plane that's perpendicular to another plane or something, and I want to find a cross product to get a vector in there, it doesn't really matter how long the damn thing now. Just get something orthogonal. That's all I need. Not the cross product specifically. Okay. Another reason I wanted to do this is just to show you. Just play with the damn stuff. Play with the definitions. And it comes out to the same answer really as you would get the other way. Okay. Let's see, so that's that. Now I want to talk about lines, and then we'll specifically at the line problem on there. So, let's see. Just got to get us used to this. If I have like what does that mean there? There's a few different correct answers here, but what does that mean? What does that tell me?
But just the vector, the direction. Just the vector.
So what does that vector do? If we put it in the right place, what does that vector do?
Points the direction.
It points to what? It points to that point, 1, 2, negative 5, cool, right? What we're going to do now is, of course, we've got to bring calculus into this. So hopefully you realize we've kind of gone through the algebra of vectors. And now we're stepping into the calculus of vectors, slowly. We first have to define what the hell a function is for vectors, right? So we're sort of mimicking what you did in algebra. You learn about numbers, and then you learn how to add them and multiply them, and then you learn about functions, and then you do weird shit with them. Well, now we're kind of going the same evolution. So I can actually have a function, a vector function. So it could be maybe like t, natural log of t, square root of 1 over t minus 1. Sure, why not? Obviously, that comes with restrictions on t inherently, right? Just like a normal function would. And the really cool thing, I'm getting a little ahead of myself because this is 11.6. What do you hope to God r prime would be? R prime. What do you hope that would be? No, come on now. R prime. Prime meaning what? R prime. You take the derivative. What do you hope it would be? Come on now.
It's 1.
1.
1 over t.
1 over t. Now this one you have to do a little work for, right? But still, it's 1 over t minus 1. T minus 1 to the negative 1/2, right? Is that cool? So then it'd be negative 1/2. T minus 1 to the negative 3/2. Cool, right? And the inside's derivative as well. That's exactly what it is, thank God. Just think about it. I can break the components of a vector up and deal with the x components separately from the y components and then put them all back together, correct? So I should be able to apply almost anything to each one separately and put it back together. And thank God that's exactly what happens here. So for example, in the x direction, if this is kind of like speed, or sorry, this is position, this will be speed. At time 5, it's on 5. At time 6, it's 6, right? So its speed is a constant 1. Every second it's changing by 1. So you should be able to treat each component separately. That's the whole idea. The x doesn't directly affect the y. They sort of act independently. And together they make the thing do some funky things, right? Okay, maybe. I'm going to try to do some Wolfram Alpha stuff. We'll see if I have more luck today. Because it'd be cool to see one of these things actually plotted out in 3D. Because it's not easy to do that. Plotting a function in 3D, not easy. So we're going to talk specifically about just linear vector functions. So they go through this whole mess here. I want to kind of break this down to what makes sense. So some of you guys might have read this part on there already, but here's what it is in algebra when I'm not dealing with vectors. This is what it looks like in algebra. So I'd hope to God that there'd be similarities in calculus. There'd be similarities with vectors. To get a line, I need, what does this really tell me? What's that really tell me? Slope tells me true, but more related to vectors. Vectors need what? Direction. So I need some kind of direction.
Failure.
Right? That's one of those questions that I ask, and I don't even know if anything's going to get close to what I want. It's, you know, it's weird. What does he want from me? Slope. What do you want? But if you think about it, slope is direction. It tells you which direction to go. It tells me I can look at it as I can even break it down to an angle then. The y and the x, I can do the inverse tangent to figure out what angle you want me to go at. It is a direction. And this is, of course, just some, specifically is y-intercept, but some starting points, right? Okay, cool. So with vectors, we have exactly the same thing. I don't know if I could, if I want to attempt, I'm going to attempt, make an attempt here, John. All right. Here we go. It's going to be interesting. So we have some point, x naught, y naught, z naught. Okay. And this is on page 721, by the way, if you want to see the computer-generated version, which is much better. We have this, which we'll name here in a second. I have some other point that is what this would be, so that 0 just represents it's the initial value, right? So when t equals 0. I have some other point, x, y, z, which is a general position for this, right? So it's got something here also. So this here, what do you think this here would be? And if you look at on page 7, you already know the answer, but this here is something I've already got up on the board. This is going to be the r of t, right? Well, they just put r in there, but this is going to be my r of t. Or my r, yeah, sorry. This is going to be my r. This is going to be, what symbol do you think I want to use for this guy? Well, r, 0, probably, right? Like my initial position vector. And then as my line moves, my position vector moves with it, right? Okay. So what's really going on here is I've got some, to get this here, I start at this and I add multiples of some vector that I'm parallel to. So I need a direction. I need to get a slope somehow. And normally the way they give it to me is they say, this vector, this line is parallel to this vector. That'll be like my slope, right? So if I have a line r of t is parallel to ABC and equals x naught, y naught, z naught when t equals 0. Right? So that's what we have. That's kind of like the setup. And if you think about it, it's exactly like y equals mx plus b. If they give me a slope and they give me the value at x equals 0, I can put together the equation of the line. Then this equation would be, let me do it more like mx plus b. So the book has it the other way around.
A, B, C, T.
Yeah, so it's going to be t times ABC. And I want to kind of do it the way the book does it. If I did it specifically like this, the t would come afterwards. The t is my variable now, right? T is my parameter. That's what I'm allowing to change. M is like this. It's a constant. It's my vector that I'm parallel to. Okay. And I can make this vector smaller or bigger, but I can do the same damn thing with slope. If the slope is 3/4, can I also make it 6/8? 30/40? Well, of course you could, but that's why it doesn't matter what form this is in. It could be any multiple of this. It just gives me a direction. That's all I care about. So it's going to be mx plus the initial point. Because isn't this what I really want here? Isn't this what I really want here? So if I let it go some amount of time, then my vector will now be here. Won't this be this plus this will equal this? This plus this will equal this here? Are you guys with me? Okay, cool. That's really all that's saying. If I start somewhere and I add something, I'll move my position vector over. That's all that equation is saying. Now, on one level, this is stupid nice, right? But you know that some of these problems aren't going to give you some of these things directly. But it's going to be a lot like when you had a problem in algebra when they said find the equation of the line that is perpendicular to this, that has the same x-intercept as this. Your first step is, okay, I've got to find a slope and I've got to find a point. So now our first step is going to be, I've got to find a direction vector and I've got to find an initial point. And then I can just throw them in. Okay. So see a specific example. This is enough abstract stuff. Let's look at that problem on the sheet here. Number 1F. The line going through R, and R was -4, -1. Going through this, parallel to, where'd it go? -1, 2, -5. So that's sort of like an equivalent in algebra saying slope of 7 and y-intercept of 2. That's where you hope to God the students go, thank God. Easy shit. Just put them in, right? So this problem is a put them in problem. So see if you can write what R of t is. So what do you got?
T times -1, 2, -4 plus 3, -4.
And just remember to put this as a vector now. So this is the point, and I need to use the vector that points to that point in my equation, right? I can't add a vector to a point. That doesn't make any sense. I gotta add a vector to a vector. Can somebody think of a way to write that completely parametrically? I mean, and what I mean by that is break it down to its parts.
X is equal to 3 minus t.
Good, so see what she's doing? She just looks at the components, right? 3 minus 1t, so 3 minus t.
Y equal -4 plus 2t.
Yeah, -4 plus 2t.
And z equal -1 minus 5t.
Okay, that's not too bad, right? So either way, you can represent it like this, or you can represent it like that. Two ways to represent the same thing.
So that's pretty much 3 lines.
This, you gotta be careful. This isn't 3 separate lines. What does this really say? This says you have some x, and really this is like x of t, right? Y of t, z of t. So my, here is my line. This is my line here. Right? That's my line. This tells me what each component must be. So really all it's doing is, notice how silly this is. All it's doing is bringing the t in and then adding vectors, which means you add the components together. So what's the x component going to be? Well, it's going to be negative t plus 3. Right? What's the y component going to be? 2t minus 4, so forth. Okay, cool. All right, how are we doing so far? Okay. So, you know, I could ask a question like, find the equation of the line that is parallel to the cross product of blah blah going through the point whatever. Right? I can just, and then you just take a second, you break it down into two parts. So I got to first get what the hell this vector is I want to use, and then I got to figure out the point from what they told me, and then just throw it together. So it's very analogous to defining the equation of a line from algebra problems. It's almost the same thing. Let me see, there was, oh shoot, one neat thing I wanted to show you. Here it is. Look at this in 2D real quick. It's always nice to look at 2D. For one thing, I can draw it better than I can draw 3D. But in 2D, what would the parametric component equations be for 2D?
X and Y.
Yeah, it'd be, in general, it'd be x equals, let's do it specifically for this. 3 minus t, I think that's what I did. No, I didn't. I did it more general. X equals x naught. Oh, let me think about it. Oh, yeah, that's right. In general, this would be like that. Oh, that was probably plus. Z equals z naught plus ct. Let me make this clear. R of t is t times abc plus x naught, y naught, z naught, right? So x in general would be x naught plus at, y naught plus bt, z naught plus ct for z. How we doing? Just looking at each component separately for the general case. Now I want 2D, so let me throw these out. Just want to do the general case real quick. 2D, I'll just throw out the z component. Okay. Between these two, can you solve for get rid of the t? Get rid of the t dependence. Take a minute and do that. Just humor me. And I don't know if you guys care or understand why I do all this weird side stuff. To me, this is where true math is. Start playing with this shit. See what it does. What would it look at in 2D? Start playing with it. Make sure you can recover what you know should be true. So what are you guys doing? Maybe take that one and solve for t. Then plug that back in there. So you get y equals y naught plus b times x minus x naught over a. So y minus y naught equals b over a times x minus x naught. Doesn't that look familiar? Y minus y1 equals n times x minus x1, right? So this is, of course, the slope. And if you really think about it, here's the slope represented in terms of a and b. So it would be rise b, run a, right? So actually, what point would that be pointing to if it started at, let's say, 0, 0?
AB.
Yeah, it'd be pointing to AB. So there's the, that would be the vector that I'm parallel to, right? Because then when I add in whatever x naught y naught is, it's going to pick it up and move it up or down. So you could have looked at it vector-wise in 2D. Of course, we decided not to freak the hell out of already freaked out algebra students with that, but you actually could use exactly the same definition in 2D. Okay. So this would act as the parallel vector, and of course that's what it should be from just looking at the 2D equivalent. It should be the vector AB that is parallel to. Okay, how's this guy doing? Okay, got about 19 minutes. Let's see. So what about this? Here's like the simple algebra problem put into vector problem. find the equation of the line. Going through oops, 2, -1, 1, and -7, 3, 5, sure. So what's really funny is the people that do really well at math, I don't care what level math you're talking about, the people that do really well at math are the people that break it down into its parts. So you only worry about one part at a time. I always see my algebra students, they worry about everything at once. I'm like, holy shit, that's why you're having so much trouble. Good God, man. Right? One thing you need is given to you. What two things do you need for this equation of a line in free space in this case?
Starting point.
You need a starting point. Well, I got two I can choose, right? Why does the starting point not really matter? I mean, I didn't say this earlier, but shouldn't this kind of be like an intercept of some kind? Like the b is the y-intercept when x is 0, that's what you get. But this is what you get when t is 0, isn't it? So of course I can change this to be whatever the hell I want to. It's just going to change what values of t give me which specific points. You guys kind of with me here? So it doesn't matter if I choose this one or that one, I don't care. T will just, I'll have to put a 5 in for t instead of a 2 to get a certain point out. Ooh. Right? What's the other thing I need? So one is I need a starting point. Which one do you want to use? Alright, the one with the smaller numbers, I agree. And then what else do I need? I need a direction. And what direction will that be? And don't get too hung up about this. When I say direction, you know you're going to be multiplying it by t. And t can be positive or negative. So direction in this case doesn't mean positive or negative. It just means parallel to what vector? What defines that vector here?
Can we make the difference of two vectors?
Beautiful. Well, the difference between these 2 points.
I mean distance. Distance.
I don't need the distance, really. All I need, so, again, I'm not going to try to do this for real. If I have a point and another point in free space, and I want the line between them, what is that line parallel to? Isn't it parallel to the vector between those 2 points? You guys with me? So all I have to do with those 2 points then is, and how do you find the vector between those 2 points?
Like -7 minus 2.
Yes! Subtract them. Cool, right? That's what we did the first day. That's what we did in the first problem. Figure out RS, you take the R point, well, in that case the S point minus the R point. Does it matter which way I subtract? No? Yeah, as long as it goes, once I pick going this way, I gotta keep going that way. So my vector, the vector that my line is parallel to is going to be, let's go this way, it's going to be 9, -4, -4. Make it 4 down. Real quick, on the side here, go with me for a second. In 2D, I can't tell if you guys are bored or don't know what's going on or some combination. In 2D, if I have the points -2, 3, and I don't know, good job. And let's say 1, -2. How do I find the slope? Yeah, right? So it does, as long as you go the same way. So like 3 minus -2 is 5, and -2 minus 1 is -3. So -5/3, right? Now what is -2, 3 minus 1, -2? And see what I'm doing? I'm just taking the position vectors and subtracting them. Or in this case, I don't even mean that, I just mean the points really. I'm getting a little ahead of myself. But just like we're doing right now in 3 space. In 2 space, what answer do I get there? I get like the vector between the two, don't I? So now I'm going to get -3, 5, which is of course what this really represents, isn't it? -3 in the x direction, 5 in the y direction, right? So this is what I meant earlier about, you could have done all of graphing in algebra 1 and 2 using vectors. Of course we're not going to do that, because you have a much simpler representation for 2D. 3D, there's no damn way to get a nice y2 minus y1 over x2 minus x1 equation, is there? Because there's 3 freaking pieces to this thing, right? So we have to actually fully represent it as, if x changes by 9, then y changes by 4 down, and z changes by 4 down also. I mean, that's another way to kind of look at this, right? Okay, maybe. You guys are so excited. Now, how did I put this together? What's r of t then? What's my equation of the line? Yeah, t times my direction plus my position vector for this point here. I love it. Bam. I really desperately hope you guys see. Maybe you are bored, which is good. Bored is better than confused. I really hope you see that the problems here are exactly like the problems in algebra. You need the same 2 things. You need a direction and a starting point. That's what you need in algebra to find an equation of the line. And you actually plug them in pretty much the same damn place we did before. Right? Okay. Let's see. Blah, 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 blah. Okay. So the examples in this section are pretty good as far as stepping it through what I just did. There's one, like example 2 is exactly like the one I just did. Let's go to this here. Let's see if I can give you, actually, give you some busy work for a second. Let's see. Yeah. Well, let me give you one a challenge here. It's like it's all a challenge. So I want you to find the equation of the line. By the way, I might write an equation like this. Have you guys ever seen anybody do that? Come on, Mike. Yeah, bring it back. Okay. Okay, where? Oh, so right there, I almost wrote that. I just want to make sure you guys know that's just math teacher laziness, right? That's a quick way to say equation. Oh, good. I got like 10 minutes. Of the line going through 1, -1, 7. On that, we get things set up on the computer.
thought I can start.
How's your second percent?
So if we were taking a test right now, I'd be drawing like that.
That's fast.
Awesome. I forgot all about that crap. Wait, who's gonna do it? Me or you? Or you? Get it? Snail? Snail?
Okay, no, I guess.
Are you sure? Did you see it?
No. It's not down here. Awkward down. Awkward.
No. That's a turtle. That's creepy.
Awkward snail?
That's pretty good. I like that.
It's pretty awkward.
What?
What about the awkward boy?
I don't get it.
It's a balloon that I'm shooting at. It's awkward. Doesn't make sense.
Why is it moving up? But you're holding it, so
What's a really strong awkward?
okay.
No, it's better. We're underwater now. Yeah. And it's floaty. Shit happens. Weird shit happens. It's upside down.
It's not. It's awkward. That's why it's awkward. You're dumb. Come on. Wow.
No, I'm not.
You need me to show you the circumference of every single snowman.
All right, guys. So, what do you still need? What do I give you directly? The starting point, right? Because I know it goes through there. So I can starting point is 1, -1/7. And I still need a direction. So what do you have to do to find the direction?
Cross product.
Cross product, right? The only one thing that I can get semi-decently quickly that's perpendicular to both of these is the cross product of those. And remember, it doesn't matter how long the vector is that I use that I'm parallel to, because I'm multiplying it by a multiple anyway. I mean, who cares? And the cross product is a specific one. That's all I need. It's going in the right direction. That's all I need. So how do you do cross product? IJK 2, 3, -1, -7, 6, 5. And who did all that business? Question.
-3y minus 3j plus 33k.
Anybody else get that? Work that through? Okay. One other one, I like that. So verification, I like it. And hopefully you guys have a way to do this kind of thing. If you really don't like determinants, like I said, if you really want to try to memorize that whole U1, U3, V1, V3, all that crap in that, I wouldn't want to. So how do I put this all together? What's a better way to write this then?
7.
Yeah, you can divide by 3 because the length doesn't matter. I like that. So it'll be 3, so we won't say equals, we'll say.
7 negative.
I'm sorry, so 7, yeah. If I could divide, it'd be great. -1, 11, cool. I like it. You didn't have to do that, but that's cool, right? So then what's your equation going to be for this line? RT equals, I like it, so T times this dude, the direction, plus our position vector for that point. And of course, Wolfram Alpha is being a dork. These things happen. Oh, I see what I did. Duh. See if it likes that. It's pretty freaky. So have you guys been playing with Wolfram Alpha at all? No. Okay.
I typed in my name and it didn't come up.
There's there's a command. So if you guys look up, guys, if you look up Mathematica command, the same people that made Wolfram Alpha, the same people that made Mathematica. So there's actually a command in Mathematica, parametric plot 3D, and then you can put in components. You can put in 1 plus 7t, negative 1 minus t, 7 plus 11t. You can put all those in and give it a range of values for t, and it'll plot the line. Right? Where it gets more interesting, of course, is where you have not linear functions, but any function. It's sort of like, remember when he did parametric equations in Calc 2, and the way I described it for my students was it was like that spirograph game. You guys ever done those? You can put the gears, and you put it in there. I still haven't really looked for it, honestly, but I used to do that when I was a little kid. My mom would give it to me, keep me busy, and I'd get tired of it after a few minutes. But now it's kind of cool to look back and say, and now for us, it's not just contained on a flat plane. We can have all these funky turns and twists in 3 dimensions now, right? So for example, on